Yeah. Well, no, come on. Shut up, Joel. Yeah, does everybody see we double counted? Right? Basically, when I sum from 0 to infinity or from minus infinity to 0, it's the same thing. Right? But I ended up double counting 0. So I have to subtract off pi of c tilde squared, because that's R of 0. What's that? Oh, C. The G is because of last lecture. Thank you. Yeah, I was using the G's last lecture. All right, so this, believe it or not, it's the least intuitive. So this is intuitive because you can get it just from squaring the original guy. If you go through and you look at the bias and square it, and if you take this bias, where did it go? Oh, fuck, yeah. If you take this difference and square it, you'll get n squared terms. It's a complete mess. But you play around with it a bit, and this just pops out. It's really nothing. I'm not going to bore you with it, but it's really simple. This is the least intuitive, but it's the most useful, because H is something we can bound very often. Well, bounding this monster is not so obvious, even though they're the same thing. Okay. So that's the form I'm going to use. Okay. All right. So, in summary, and this is what we call it's also called the variance. Question? There must be a question. What's the question?
Just like this notation with H by C of X, is it like H composed with C of
No,
X?
no. Dot products, everybody, dot products.
Because in this notation,
No, dot product. When I multiply H and C tilde, when you multiply two functions together, you get a function, right? And so when I have a function here, and I write pi of the.
Okay.
Yeah. That's just a product of two functions, right? I'm just multiplying two functions together, and then taking the dot product with pi. It's really useful to have this notation. Okay.
Okay.
Yeah.
It's just another notation.
No, it's not another. No. I'm going to take pi. No, not at all. It's nothing new. Every function is a column vector in the notation we're using. And if I take two functions, I can multiply them together. I get another function. That's another column vector, right? And every probability mass function is a row vector. And so this is just a standard row vector, column vector notation. Nothing new, okay? It's just it looks a little bit funky, I agree.
Yeah, we just have two column vectors now.
No, we don't. No, we don't.
H and C.
No, they're not. No. We're multiplying two functions to get another function. Now, pi of HC is equal to pi of, I don't know, f. Have we used an f? Where f of x. I just want to make sure this, nobody thinks I'm extending notation. That's all I mean. Yeah, it's just element multiplication, so it's nothing new. Okay, it's not. Yeah, it's good to slow me down. I'm not complaining. All right. So in summary, it's like roughly speaking. I guess we can kill this. Again, heuristically. And I could write, as an approximation there, and it's not a heuristic if I say in distribution, you have this approximation. You just have to be very careful what you mean. But you've got the normal notion of bias over here, and then you've got this this thing over here. And that's a 1 over n, and that's a 1 over square root of n. So that definitely dominates, Of course, you want to, when you do simulations, you want to make n large enough so that this goes away. So you're going to have to, go for a long time. But the main thing you worry about is this 1 over square root of n term. Because you go out 1,000,000 terms, you only divide it by 1 over square root of 1,000,000. So it's, and this thing here could be 1,000,000. I mean, gamma g could be, it really can be huge. And I'll give you an example right now. Do we have a chance? Yeah, go on.
So we started out with an algorithm to compute eta, and we derived gamma c squared, which seems to be independent of the algorithm. Is that correct?
No.
It seems like as soon as you do the transition matrix, you can compute it.
Oh, no, if it's a finite states Markov chain with under 1,000,000 states, invert a matrix, you're done.
So like it doesn't necessarily, so for example, this is true for you just had a matrix, for example, that satisfied the certain properties that the transition matrix satisfies.
Well,
you could compute this number.
Which number? Well,
gamma c squared.
Well, the thing is that computing this is way more complicated than computing that. So we're only going to hope to get bounds.
So what would it mean in other applications? Like if you, I'm sorry, that was kind of general, but if you could still principally compute that number, right? If you just had a matrix and you had a cost function, and the matrix satisfied the same properties that the transition matrix satisfied.
Wait a second, I don't understand. I need something more concrete. That's too vague for me. But we're gonna see, again, I keep referring to reinforcement learning way to the end, but that's just because we're talking about simulation. This will be a parameter in some algorithm, and we'll find that the best you can do is square root of n, and very often it's slower than square root of n. Very often instead of 1 over square root of n, it's 1 to the n to the 0.00000001, because it's a bad design, But and you end up using the same machinery. You get a formula that involves Poisson equation again. That's not answering your question. But.
Yeah, I mean, I don't know, just because we started out with this algorithm to compute eta.
Well, just standard Monte Carlo. Remember what eta n is. And that is not the only way to, estimate the mean. That's just the way. In fact, I think it's really an open area about the best way to estimate the mean of it. I think it's
because we ended up with something that's going to help us analyze the performance of this algorithm. It doesn't depend on the algorithm.
No, it depends on the algorithm. We only get this. Now this algorithm gives you this formula.
Okay.
If I used a different algorithm, I get a different formula.
Okay, yeah.
There's no question.
That's
Yeah. Oh no. I mean, should I give you another algorithm? There are all sorts of algorithms that converge.
Yeah. Well, I see why it depends.
Yeah.
On the algorithm,
Yeah.
But
yeah.
If you want.
Well, just for the fun of it. I mean, here's one. I was just on my bike ride to work today. I was thinking, I wonder if I should give a homework problem where you guys all fool around with different things. How about, here's a crazy one. Eta hat n plus 1 equals some momentum term times eta hat n minus eta hat n minus 1 plus some constant k over n plus 1 times eta hat n minus c of xn. How's that? There's a fun one. I want you guys to simulate this later on. I know it's stable if you make m really small enough, I'm pretty sure. But you have the signs wrong. I don't know. And you can imagine you can kind of imagine this might work because if it converges, you're averaging out a lot of these guys, and if it converges, then, oh no, I missed a term. Yeah, I missed a term. Because if it converges, that goes to 0, that difference goes to 0, there's a hat missing. And then here you're averaging a bunch of C's. So it kind of makes sense that you get to this. So, in March, I will give you an explanation of why this, if it's stable, will converge. And it may be that with knowledge of the Markov chain, you can choose K and M to get much better convergence rates.
You should.
What?
You should be able to.
No, I don't know. There's something called, we'll see that maybe that's, what I'm saying right now is stupid. I don't know. I'll have to think about it.
Yeah.
No, it's really deep. Because,
Find some other just regular optimization type algorithms, you can often find optimal parameters for your momentum terms.
Yeah, you'll see it's different context. That's optimization. This is really different. The thing is that, for IID sequences, it's really obvious the best thing you can do is average. And the reason is because every sample has the same information. For Markov models, it's different because the initial samples are super biased. The initial condition has a lot of it, it messes you up a bit. So it might be useful to do something to burn out the transients really nicely with some crazy thing like this and emphasize in some way later terms. But I mean, to try to get a formula for the variance of this monster, I won't give that to you as homework, I promise. So anyway, it's interesting. I'll bet I'll come to you next week and say, no, it's ridiculous. There's no way you can do better than this. I'll have to think about it. Yeah, I'm not sure. Okay. Anything else? Oh yeah, I wanted to give just one example and then we can break. So, does this thing work? Oh, it does, cool. Okay, so MM1Q. So MM1Q is this really boring Markov chain where you just go through, here's K, here's XK, and it just bubbles on down and bounces around. And the slope there is approximately minus mu minus alpha. So if rho is less than 1, it means that alpha is less than mu. And so there's a sort of mean drift, which is negative. Right? I don't know why this phone keeps ringing. All right. So we know everything about this problem. That's why I brought it up. So we know. Well, I don't think I've told you that the steady state distribution is. Have I? The invariant PMF. It wasn't the homework.
Sorry, the notes.
And the notes. Yeah. So the pi is geometric. So it's just geometric. And actually, there's a really cool way to see this. There's something called the detailed balance equations, which we talked about. Okay, I'm just putting an exclamation mark here because it doesn't hold very often. This is a very, very special Markov chain. So if I made this different at all, suppose I made this uniform between -1 and 1, the detailed balance equations wouldn't hold. Suppose that this was equal to -1, 1, or 2 with different probabilities, then this wouldn't hold. It's only for this case. I could allow 0 as well. This could take on values 1, 0, -1, and the detailed balance equations would hold. But it's very special. But can you all see that because this holds, it's obvious we have invariance? Can you sort of imagine what happens if you sum both sides over x? This implies see, this is the sum you look at when you want to check invariance, right? And what happens when you sum this over x? The summation, the probability of going from y to somewhere is 1. All right, so that's pi of y. So that's a really nice trick. If you have a Markov chain, you can actually check this condition, which turns out to be really easy in this case, because for every y, for every x, you only have to check above you and below you. Wherever I am, I can either go one step up or one step down. So it's very, very easy to verify this condition. And once you do, then you get, invariance. And in this case, anyway, so we know the invariant distribution. That's one thing we need to know for this. And God, it's tricky, I mean, it should be easy then. I've got, I'm going to take c of x equals x. And so pi of c if you remember how to take a sum of a geometric and an n, you can use moment generating functions or something like that. Forget it. I'll give you the answer. It's go over 1 minus rho. All right. Oh, yeah. So you can work that out. From this form, since pi of n is 1 minus rho to the n, you can get the first moment. And then, so then you can go through and try to compute the variance. And you've got to work out the second moment. And does anybody know what the second moment is? I've got a cheat sheet here. Oh shit! It's roughly twice the mean squared. So this is what I call eta, right? Okay, so the variance is approximately twice, and maybe that's. I mean, anyway, I don't care if that's wrong. Maybe it's 3 times. Maybe there's no 2. I don't give a damn. What I'm trying to make a point of is the variance is of order eta squared, the mean squared. Now, how about this monster over here? Pi of hc tilde. What's h? You can check this yourselves. You can just work it out yourselves, that pH equals h minus c tilde. And notice, by the way, it's greater equal to 0. That's really useful, because the bias involved h minus p and h. So the bias is actually, anyway, go look at your notes. Very often, you can find solutions which are non-negative when c is a function that blows up. That's a general principle we'll see. But then you go through and you see we've got that mu minus alpha. Let's write this out. That's 1/2. I can take the mu outside. You know, just so you can see that I've got a 1 minus rho here again. All right. So I've got when rho is close to 1, the mean blows up. When rho is close to 1, the second moment, the variance blows up far faster, 1 minus rho squared. Now I'm going to be looking at I'm going to be taking this and multiplying it by c tilde. This horrible mess. I forgot the pi of x. I just want to emphasize rho close to 1 because that's when things get nasty, okay? So this other term that comes up is this thing here. I've got my c tildes right there. And then I've got these terms here. X squared is a lot bigger than x for large x. So what I'm doing is I'm throwing away everything and just keeping the cubic term. You could say, why are you throwing away the eta term? Well, I can justify it. It just takes about 100 pages of notes. So you can, I guess, maybe I'm cheating with the constants. Hold on. Because the negative sign does reduce the constants a bit. But there's some constant I can come up with to get that. And I can even give you the constant because in general, it turns out this whole thing is 8 times eta to the 4th.
That's series converges.
What?
This sum right here.
No. Oh, look at it's geometric.
No, the cube.
No, look. Pi of x is rho to the x.
I'm saying this sum right here, x cubed times pi of x.
Yeah, take a look at pi of x.
Pi of x is that, I know.
We can imagine.
But x cubed times that.
Yeah, but think about it. No, think about it. It converges really fast, right? Because this is going to 0 geometrically fast, and this is just going. It's just a cubic. All right. So I've got a geometrically decaying term times the polynomial. So I could put in any polynomial here. It's finite. Okay. Yep. And so so it's finite, and it turns out it's like a to the 4th. Okay. And so that's the thing, is that if you haven't had a course in Markov chains, you'd look at the variance and say, oh wow, my load is 0.9, eta squared, is 100. I can go for 1,000 samples and get a really good estimate, or 10,000 samples, right? But it's not a to the squared, it's a to the 4th. And you can have, with rho equals 0.9, you can have 1,000,000 samples and get a shitty estimate. It's the most boring Markov chain on earth, and it's absolutely horrible. And that a to the 4th is deadly if you've got a high load. The Markov chains are really, really treacherous. And this is a really good example. The simplest Markov chain there is. So it satisfies this detailed balance equation, which is the strongest in the world. It's called reversibility. It's also geometrically ergodic. So it turns out that if I look at p to the n x to y, that converges to pi of y geometrically fast. I can't prove that to you using spectral theory like I did for finite states with Markov chains, but you can prove it using different methods. It's geometrically ergodic. So it's reversible, geometrically ergodic, everything's nice. This is a tiny function, considering that pi is a geometric distribution. So it's got very light tails, but the simulation is hell, So anyway, you can see more on this in my book. And there's a lot more horrible things about this simple example. So that's just it. All right. So, we'll come back to this. I mean, because I want you, when you give me simulation results, I don't want point estimates. I don't want you just to hand me that, and say, hey, I solved the problem. So I want you to use this result to have more thoughtful simulations, because we're going to do a bunch of simulations. Every homework problem is going to have a simulation from now on. And I want a histogram, or I want confidence bounds. And the only way you can do that is to run independent trials. Do a run for 1 million samples, do it again, do it again, do it again, do it 1,000 times, and you'll see a beautiful bell curve. And you'll be able to estimate the variance. You'll be able to estimate this guy here. Yeah. Okay. Cool. So let's take a break. And have a slight change of pace.